Okay. Okay, so the first thing we'll be covering today is a curve simulation preview in Grasshopper for more of the wearable side of things. So with this one, we'll be able to take this curve, and it's going to update. Turn this off real quick. We'll be able to simulate the curve surrounding this figure, simulating as we've added a couple rules to it to shorten as we progress through the animation. So we'll see with Kangaroo, we'll define some parameters for what is going to be happening to the curve. And then through the simulation, it'll be affecting that to change it as we move along the timeline. So we'll turn that into a wearable piece for the first workflow. And then the second one, which is a little bit smaller, but just to show some of the mesh capabilities of this.
Hey, RJ.
We'll be able to take an input surface such as this one, which has some complex curvature to it. It's nothing simple like a cylinder or a cone. We can't just unroll it to make it flat that simply. But with Kangaroo, we can simulate the mesh by keeping the, let me see.
Hey, RJ, you aren't sharing your screen.
Oh, is it not sharing?
Yeah,
I'm recording,
sorry.
but not sharing.
Thank you.
Yeah, you're welcome. Thanks for letting me know. Okay. Oh, so, well, we'll see. Okay, so for everyone on Zoom, what I had just mentioned a second ago was this workflow simulating a curve as it animates around this human figure. So we'll look at that one first, and then we'll take a look at this flattening this mesh if you wanted to take a complex curvature surface into a flat pattern that you could laser cut or print out and then fold back into the shape. So we can take this complex shape with all these faces on it, and we can kind of flatten it with Kangaroo. So we can see here the outline being generated as the mesh actually simulates and becomes flat on a plane. So we'll take a look at that one second. Okay, so I'll open up the file that I shared with everyone and we'll get started on this workflow. So with this file here, we have a couple inputs, or I think, yeah, you should have an input with a person on it. It might be different, I forget, but I have this person and this block around the head. So with this first workflow, we'll be able to parametrically change the curve that goes around the body using this box as a volume to populate some points in. So a lot of the workflows we've done previously in other classes, we always use, normally points to start out with, and then we'll use those points to affect something else. So in this case, we'll be using the points to affect a curve that is randomly generated inside this area, which is kind of around the head region of the figure. So with the first thing we'll do is just simulate or kind of populate this box with a cloud of points. So first thing we always do when we're populating is define the region that the points will exist in. Easiest way to always do that is to use the bounding box, which we've used a couple times in the past. In this case, we have a cube, so the bounding box is going to be the same shape as a cube. But if we had any other kind of shape or some shape that you sculpted around the form to act as the boundary region, it's always best to put the bounding box because it's a lightweight kind of region that'll encompass the entire shape. And for the populate component, it needs a simple region like this. So if you had a more complex mesh that was more than a cube, we couldn't use that as a region. So it has to be this bounding box. One thing I'll point out is the bounding box, if you right click on the icon in the middle, it has two options. So right now as it comes in, it'll say per object. So if we had 5 objects in the scene, it would put its own bounding box around each of the 5 objects. But it has another option, it's called union box, which will put a bounding box around all 5 of those objects. So 2 different options there. Right now, since we only have 1 box, we can just stick with per object because it's not going to make a difference. So once we have a box, and let me put it like this so we can see everything. Now that we have the boundary region, we can go ahead and populate it with points. So as we've done in the past, there's 3 options: either populate geometry, which will go on the surface, of a shape or a mesh. We have populate 2D, which will do it inside a 2D region, or populate 3D, which is what I'll use for this 3D box. And with this one, we have the 4 inputs here, which will only use the first 3. So the first one is the region. So that's the box that we'll be defining it in. Currently, it's probably really small down here, but we'll use the new box that we created as the new region. And we'll see it'll bring the points up into this new box. So we have a couple controls over the populate 3D. So the next 2 will be the count number and the seed. So the number is sort of important to control like how complex this curve is going to be. Basically, what we can do is take this random cloud of points and just draw an interpolated curve through it, which will give us the curve that we can do the simulation on. So in this case, with 100 points, if we were to draw a curve through all of them, there's a couple ways. You could either use the interpolate, which will give you a smooth curve, or you could use polyline, which will give you a very rough curve. Right now, we're going to be using interpolate. And I'll show you what it looks like now, but we'll do a couple steps before the interpolate actually comes into the main function of this script. But basically, if we plug in the points to its vertex, the vertices as a list, we'll get a curve, but it'll be very messy. So we'll do a couple things before going to the step to clean it up a little bit. So the first thing we can do is take down the number of points. So right now at 100, there's a lot going on. So we can grab a slider and say we can go from 1 to 100. So remember, doing a slider, you always put the lowest bound, 2 dots in the middle, and then the upper bound. And that's usually the easiest way to get a slider. And that's not what I did. So there's 1 to 100. Okay. So we can plug in the slider to the number, and we'll see now we only have 1 point in the scene. Since we only have 1 point, though, the curve is going to fail because we need at least 2 points to draw a line and more if we want a smooth curve. So I'll just bring this up, maybe around 12 or so. So it's not that messy. It's still quite simple.
So is it creating that one line?
Yeah, it's doing right. It's doing one curve, and there's not much kind of intention to how the curve is being formed at this moment. The points themselves do have a set list or like step when you do the populate. So it's going from 0.0 to my case 0.11, so 12 points in total. But those points are randomly placed in the scene. For this workflow, I'm going to do something different to make it look more symmetrical and intentional. But there are ways in Grasshopper to organize points if that's what you're looking to do first. I think if you have pufferfish and a couple others, there's a lot of different ones. With Grasshopper, that comes with it, we have a sort points by Euclidean coordinates. So you could sort it, I believe this is under the the vector is a vector. Vector points tab. It comes with it a sort points. And this could take all the points and organize them first by X, then by Y, then by Z. So if we were to do that and then plug it in, now you see we kind of getting it flowing left to right. So that's kind of the simplest way to sort points if you were looking to do something like that. So that's good to know. And then since you asked the question, I'll cover a few other ones as well. Forget. These are 2 others. They come with a plugin called Fennec, which you can't kind of really see with that. It has some other interesting things. We haven't covered this plugin, but this has a couple other ways to sort points. So this first one does it from sorting the closest points together first and getting longer and longer. And then this other one, ascending, descending. So you can set the order. Whereas with the one I showed from Grasshopper, it does X, Y, and Z. With this one, you could set that order and kind of do it more custom. Yeah, FPNNEC. Yeah. You can also sort points along a curve. So if you have a curve already made, you could take that curve and sort the points from start to finish on that curve, which is a nice one. Or I believe this one, yeah, this is with pufferfish. So I think this one's the most useful because you can define your list of points and then you can set the starting point that you want and it'll search from that starting point to the next point to the next point. So it's not like an XYZ sorting, it's more organically sorting from what's closest to what's farthest away. Yeah, so if anyone wants to know about sorting points, those are all some nice resources. Okay, so before going to the interpolate, we'll do a couple things to make this cloud look a little more intentional. So with pufferfish, one of the main features of pufferfish is a thing you can do called mirror cutting. So you can take pretty much anything in Grasshopper and cut it based on a mirror plane. So you could take a mesh and mirror cut it. So you could get symmetrical halves. You could mirror cut curves, domains, numbers, but in our case, we'll do the points. So we'll just take the points from one half and mirror them to the other half. And then when we draw the interpolated curve through it, it'll look a lot more symmetrical. So where is it? Yeah, so yeah, mirror cut. Okay, it's mirror cut points, not mirror mesh point. So yeah, mirror cut point, and we can grab this component that allow us to mirror the points over a middle plane. Yeah. Oh, and I guess for you just came in, but the file that I'm starting to use with is in the Discord. If you saw it, you got it. Cool. Okay, so with this component, basically all it needs to work is the cloud of points and the mirror plane. So we have the points, so we can plug that in to the P here, but it won't do anything just yet. We'll have to set up the actual mirror plane for it to cut along. So yeah, if everyone's there, the best way to do that. So we have the bounding box from the beginning. I'll turn this back on. The bounding box can tell us a lot about the scene. So with the bounding box, we could find the center point of this box and then define the mirror plane based on that. So if we were to ever move the box around to say a different part of our figure, the center point would follow along with it and the cutting plane would also follow along. So that's a good way to always keep your script fluid and being able to update if you make any changes in Rhino. So in order to find the center point of the box itself, we can use a component called area. I wish there was one just called center, but we could either use area or volume. It really doesn't matter in this case. We don't need the area or volume number, but what this component will do is it'll also give us the center point from that calculation. So you can use area or volume, either one will give you the center point, and we can see that one coming up right there. So with that point, we can define the plane to cut it along. In this case, since I have the figure facing this way in the scene, if we look at our coordinate system down here, the plane going straight through the figure would be the YZ plane that cuts straight down the middle. So we could take the center point and pipe that into the YZ plane. So anytime you're using the planes, the XZ, the YZ, or the XY, the only input they need is the point to exist on. They already have the orientation set by the plane you pick, but all it needs is the center point. So we can use the center right there to construct that plane. And it's probably really small, but it'll be coming up right in here as a plane. So that's not too crazy. And then once we have the plane, we can plug that into the mirror plane, which is that second input for the mirror cut points. And
So area, usually just when you plug it in automatically find the center point.
Right. Yeah, area or volume will both find the same center point. I kind of use them interchangeably because I never usually need the area or the volume. There are, right, I just use it to find the center. There are components that find centers, like if you use the centroid component, but that's only for flat polygons. So it can't be used in this case for a 3D shape. Okay, so now that we've mirrored the points, we can substitute these points for the points already going into the interpolate curve. And doing this will change it and make it look a little bit more symmetrical. So that's the first thing to do. The second thing is, let me see. As the interpolate curve comes in, the input for periodic, which defines if the curve is closed or not, always comes in as false. So one thing we could do to make it actually finish off and become perfectly symmetrical is to grab a toggle component, and the toggle will allow us to change the Boolean in the periodic input from false. We can plug it in and double click it to set it to true. And then we'll get a much more symmetrical result just because we closed the curve off.
Wait, did you make those points yourself?
Yeah, so the points are defined by this populate 3D. So we're just generating them randomly in space. Let me see. And you bring up a good point too. One thing I forgot to mention when we were creating the populate 3D is the count input is important for kind of the complexity of the shape. So I could pop this up to 30 and we'd get a much more complex curve, although it's still symmetrical. But one thing that is super important for making this procedural is to add an input for the seed here. And the seed is the number that sets the randomness of where the points are existing in space. So I'll just duplicate the slider here. And right now the seed comes in as 1 by default. So I'll plug in my slider. So with still the same 12 number of points, we can change this slider to be a different number and we'll get a very different random distribution of points in space. So we'll come back to this input later on and change this one to get wildly different results from the same code. So all we need to do is change this slider and we'll get infinite number of different outputs. So that's a nice one. So that, yeah, the seed is always super important. And any component that has a randomness to it, there's always a seed input. The populate points have it, and the random component also has it. But the random is built in to this populate. Okay, so coming off these curves, right now we'll just prepare them for Kangaroo itself. So in Kangaroo, it takes a couple different data types. If you have a piece of mesh, that can go into Kangaroo pretty well. But this interpolated curve isn't going to work too well for our understanding because we can't really break it down if it's one continuous curve. So the first thing we'll do before adding it into the logic of the Kangaroo plugin is to divide it into multiple smaller segments so we can use those segments to either grow or shrink the overall curve. So the first thing in order to do that is we'll just go ahead and divide the curve. So we have this divide curve component, and this will just cut it into any number of equal length segments. So if we plug the curve into that, the first thing we'll get is it'll divide it into 10 segments, which is pretty small. And if we use this going forward, we'll have a very low resolution and it won't even look like the input. So we'll want to bump this number up. And I've used a number of 200 for this case. But you could pretty much go with anything. I'm just trying to choose a number that's low enough for the simulation to run quickly, but high enough so we still get some good detail coming out. And again, with the panel input numbers here, to add a panel, you can either use the panel from the input section up here, so you can grab it there and type in 200, or to search for a panel, we can double click on the canvas and just do 2 forward slashes, and then type in 200 and get a panel like that. So the only reason I'm using a panel over a slider at this point is because I don't want to change this number later on. There's not really a point to. It's got a good amount of detail with 200 points, so we're just going to leave it at that. Anytime I use a slider, that's a good indication that we'll probably come back and change it later on and add some input to it. But this one's going to stay static. So coming off the points, we've taken the interpolated curve, we've cut it down into just points now, and we'll want to rebuild it back into just a line-by-line segments. So we can use those segments again in Kangaroo. So the first thing we can do is use a polyline component, and that'll take our points, make them into curves, so we plug the points into the vertices, and this will make a faceted curve, so we have some points, some kinks in the line. And one thing that's important with either the polyline or the interpolate curve is they always come in with, in terms of the interpolated, it's called periodic. In terms of the polyline, it's called closed or not. They always come in as false, so it's always a broken line. In this case, we'll want to turn it to true again to close it off. So again, we'll grab a Boolean toggle, set it to true, and we'll see we have this little gap at the bottom right here. Plugging in true, we'll close that gap off and make it a full curve. Okay, so now that the curve has segments to it, we'll just extract those segments from it. So now we're going to go into the Kangaroo section. So I'm just going to group this part off. So that's the first part, just creating the actual curve input itself. So we'll build up Kangaroo now. So I'm going to pull up the Kangaroo tab. And with Kangaroo, there's a couple important things to notice. The first one is in this main section. This is where all the computation is actually going to happen. So we have a choice between a couple different solvers here. And what the solvers will do is take the input data, which in our case is going to be line segments and points. And it'll also take into account some goal objects that we set. So the goals could be anything like stay apart from each other or shrink or stay on a piece of mesh. And all the goals are listed to the left of the main drop down right here. So we'll get into those in a second. But the first thing, the one we'll grab out of here, there's a couple different solvers. They all do slightly different things. The bouncy one has some momentum with it, so it carries some weight behind it. The generic solver has just a start button, so just run. The zombie solver will not show you any iterations until it finishes, and it will show you the final iteration. All different, outputs of the same thing. But in our case, we'll use the step solver, so we can have granular control over the movement of the simulation. So I'll just grab that step solver and pull that out. Okay, so with the step solver, you'll notice the first input is the goal objects, and we'll get to those in a second. But before we start that, we do want to look at the animate put down here, and this is the one that we'll actually use to start the simulation and stop it. So with this one, all the animate slider needs is, if you read that little description down there, if it's false, the simulation goes back to the reset state. And then if you start adding up numbers, it'll start moving more steps down the line. So we can do both of those with the same slider. In binary, false is equal to 0. So instead of setting it to false with a Boolean button, we can just use a slider that starts at 0 and use that 0 as the reset. So I'll just grab a slider from 0 to 100. I'll keep it simple. And plug that into the animate component there with the input. So right now it's just sitting at its reset state, and we'll just leave it there as we add the goal objects into it. So as I said, for the goal objects, a lot of things in these drop downs right here for different things that you could be doing if you wanted to find angles or coplanar things or kind of physics-based rigid bodies. But the one we'll use today, we'll use 3 different ones. The first one will be the length. So with this length component, we can set the segments of the curve and we'll give them a length to shoot for. So if the length is bigger than the segments, they'll all try to grow to that length. And if it's smaller, they'll all try to shrink to that length. And the solver is nice because as they all shrink, they'll affect the curve next to them. And as all these segments are trying to interact, the whole system will be moving as one. So that's the first goal that we'll define for this system. The next one, let me find it. Okay, so under, it's not gonna tell me which one it is. For the goals collision dropdown, we have a couple different options for collisions here. And the reason why we're using this is because we don't want the curve to kind of collapse in on itself. We want it to know about where its neighbor points are and stay away from them. So we don't just get a jumbled mess, but we still get something useful on the other side, on the output. So we'll use this sphere collide in conjunction with the points that we defined to set some boundaries for all the points there. And then the last one we'll use is under collision as well. So that's called the solid point collide. And what this one will do is it'll keep the points either inside of a mesh or outside of a mesh. So we want this curve to be interacting with its environment as well. If it was just simulating in space on its own, that wouldn't really tell us much or do much for the validity of a workflow like this. So we have that input mesh that I've given you all of the figure. So we can use this solid point collide to keep the points off of the mesh so it doesn't collide through the person. Be a lot less realistic if it just clipped through the mesh. So we'll keep them outside of the mesh. So we'll use these 3 as our goals for this curve system to follow. So we'll pipe all these into the goal object input. And the easiest way to do that is to grab the merge component, just like we did anything else. We'll take all these 3 goals, put them into the merge, and then they'll all together as one go into the goal object input. So with Kangaroo, you don't have to be too thoughtful about the organization of these goals. They can all just get shoved in to the same merge. It doesn't matter what order they're in, and we don't have to follow any of the tree dynamics like we've been looking at in some of the previous workflows. They can just all, as a flat list, go into the goal object input. Right now, they come up as null. We'll have to actually set some of these inputs here for them to start defining simulation. So with the solid point collide, couple easy inputs here. We just need the points, and then we need the solid mesh to stay off of. So we have that mesh from the beginning. So I'll just preview that back in. So we can just take this mesh and add it into the solid input. So this is the closed B-wrapper mesh that the points will be able to recognize. We'll also want to define if the point should stay inside the mesh or outside of the mesh. So in this case, we want them to stay outside. So we read this here, the points will be kept outside if it's set to false. So we'll grab another Boolean toggle, comes in as false, and add that right there to the in section. Yeah. So the points we'll need for this is we'll actually take the points from the final curve itself. So everything before is just setting up the final curve. So we can take the points from the divide and plug those into the points here. And nice thing, actually, the same points we can use for the sphere collide as well. So we can take the same points and pipe them into the points for the sphere collide. So we'll use the same points for both of these. I'm just going to move this polyline up a little bit so we can see how the wires are flowing so nothing's overlapping. Okay, so what was the question? Right. Yeah, so the sphere collide will use the exact same points. Yeah, exact same points. Because all we have now is the points and the segments, and that's the only two things we'll be affecting for the simulation here. So going into the segment part, we have the polyline, and now we'll just want to break that up into all of its individual line segments. So we can use the explode.
Wait, where's
Solid point collide. So if you're in Kangaroo in the collision drop down, same as the sphere collide, it's just at the bottom there, I think. Solid point collide. Oh yeah, it's right above sphere collide in Kangaroo. Okay, so with this explode component, if you've already done this, comes across. So we'll just plug the polyline into the explode component, and that'll take it and it'll divide it into all of its segments. So again, we have 200 segments because we broke it up to 200 over here. So now we actually have the segments individually in this list. Okay, so with these segments, we can plug those into the line input, as this one asks for only lines. So now that we have that, we can plug that in. And
So we can't do the whole polyline.
right, so we break it up because we'll want to actually, for this definition, control the length of each of those polylines themselves. Yeah, if we just did the polyline as a single polyline curve, then we would not be also referencing the points themselves. We'll have the individual points and the individual line segments that will both be affecting. In this workflow, the points and the lines, line up as a list in Grasshopper. So we have 200 points, 200 segments. So everything will work well in the simulation. I think if we did it the other way, like we plugged in a single line with 200 points, the points would kind of be abstracted from the curve and not match up, and we get a weird simulation. So with those segments, the last thing we need for this line goal is the length of the lines. So if we said the length of the lines are the current length, nothing would happen in the simulation too much. So we can add a slider that will affect the length for each of the lines, and then in the simulation, we'll see that reacting based on our slider. So one thing we can do is we'll actually need to take the length of the line segments themselves. So with the length component, we can plug in the segments and we'll actually be told the length of each of those segments. I'm just going to pull out a panel. We can see we have 200 different length measurements for all the segments here. Okay, so as we've done this equally, we've divided it into equal segments. All the lengths are pretty much the same. In my case, they're all around 41.7. So we don't need the length of each segment exactly. We can kind of find the average of them all, since they're all pretty much the same, and use that single value as the value that we can react upon for the length goal. So we can grab this component called average, and that'll just take an entire list of data. Doesn't matter how long it is. If we connect those two together, I'll see I now have one piece of data. It looks like the average is just at 41.64. Okay, so now that we have the average length of all the lines, if we want this curve to expand, we could increase that value and plug it into the length. And if we wanted it to contract, we could lower the value and plug it into the length. And we'll see it react when we actually start the simulation. So in order to do that, the easiest way is we could just multiply this value from anywhere from 0.1 to 1. So 4 to 2. So if it was 2, it would grow. If it was 0.1, everything would shrink based on the multiplication value. So we can plug in that average to either the inputs for the multiplication. Which one? The average? Yeah. Oh, just multiplication. So you could type the word, or you could just do Shift 8 and get the little star sign, and it should pop up as well. Okay, so once we have the, the multiplication component in there, we can just grab a simple slider. I'm going to do 0.1 to 2, so we can either shrink it or expand upon it as we change that slider. So plugging that into the multiplication will affect on the average value, and now all the curves will try to shoot for a length of 4.2 in my case. So they went from having a length of, was it 46, to now they'll all try to finish at a length of 4 when we do the simulation. This will be over many steps, so it's not like instant shrink from 46 to 4. It'll probably take 500 steps of the simulation to actually see it get to that size. So with this value, we can actually use this both for the length and for the radius of the imaginary spheres around each point, to tell all the points to stay apart from each other. The reason why we can use the same value for the length and for the radius is because as we shrink the segments of the curves, we also want that radius to shrink so that they both line up. It's nice that it's the radius because since the points are at the ends of all the lines, if we had a sphere around this one, the sphere would only reach here, which would be perfect for the next one. And all those spheres would kind of stay off of each other. Right. Yeah, we'll hit start in a second here and actually, see it all happen. I can also visualize what those imaginary spheres are. So if I set the multiplication to 1, this is the starting length of all the lines, and we can see each sphere, just perfectly hits the next point around it. So we'll keep all those points off of each other. And as we shrink the length, also the radii will shrink. And when we simulate it, we'll also see the curves themselves shrinking as well. I just use the base as the same points. I'm kind of just visualizing what sphere collide's doing. We're not going to use these spheres at all, so just a visual thing. And I guess if you also want to visualize it, you don't have to for this workflow, but if you want to, I'm using the mesh sphere from the mesh tab, only because the mesh sphere seems to work faster than sphere itself. This one is a little bit more taxing on your system to do the BREP than the mesh for some reason. So since we have a lot of points, I use the mesh sphere. Right, so this one is just a lot simpler. I think the other mesh sphere, you can control the number of quads on the surface. So we just need this. You could use a cube for this as well. The cube would just be maybe abstracting it a little bit too much from the radius value. So yeah, so we don't need those spheres, but they're just nice if you want to visualize it. Okay, so now that we have this all set up, we have a step solver. So it might not be as cool to see as one of the other solvers, but let me set this up quickly. You don't have to do this as well. It's not for the workflow. But this is one of the other solver types. So with this one, all I have to do is hit a button and it'll start. With the other one, we can move the slider and like fine grain control what we're getting. But just to show like what'll happen now that it's all set up. It should work. I'm also going to flatten for everyone. I'm going to flatten the output of the merge just to make sure it's all on the same list coming out, just to make sure. But okay, now we can actually see once I hit start, we'll see it goes really quickly. But all those curves are trying to shrink to that length of 4. So I'll hit the reset button again and we'll see it hop back. And over, let's see, 540 iterations, it happens super quickly. This is what we get to, kind of the settled state. So all the curves are now that 4 unit length. But again, this is happening really quickly and we can't really get anything visual out of it. So that's why I went with the step solver for this workflow. So I'm just going to stop this and put it over here because we don't need it. So actually going with the step solver, what we're able to do is right now at 0, this is resetting. So same as pressing the button to reset, at 0 to reset. I can slowly move this slider and we can see the curve move with me. One thing I'll mention is right now it's also happening pretty quickly. I'm only at iteration 8 and it's already gotten super, super small. I kind of want it to go a lot slower than this. So we do have some more control over how the physics is working in our little environment. And one of the ways that we can do that is with the sub iteration input. Right now, so each frame I would say is an iteration of this solver. So every time it's trying to get closer and closer to the goals that we set. But in this case, since the sub iteration number is set to 10, it's doing 10 steps in between each one of our single steps. So it's going a lot quicker than I would like to see it. So what we can do is just grab another panel, just set it to 1. So one step that we put in is one step that the solver is also doing. And just add that into the sub iteration. So now when we pull this slider, we'll see that the animation is happening much, much slower. We have a lot more control over where we want to stop it. And I'm not sure if you can go decimals for the sub iterations, but you can try if you want. I'm just going to leave it at 1 for now. Okay, so coming out of the step solver, this last output here is all of the outputs from the goal functions. So this is pretty much defining where the curve is after we stop. So right now, if we look at the list, we'll notice some of the inputs are null, which if we were trying to reconstruct the curve on the back end back into a single interpolated curve instead of 200 lines, is the first thing we want to do is just clean the list so it looks like this, tree saw kind of icon right here. And what this one will do by default is just remove any nulls from the tree. So if we have any bad data, it'll just take it out and clean everything up for us. So we can plug this output into the data tree input here. And this will just go ahead and clean everything up. So again, we'll only have 200 line segments, just like the input. Now it's just on the output side. So yeah, at this point, we still have the 200 segments. So what we can do is just join them into a single curve. And for that, we can use join component to join all those individual segments into one curve. So plugging that right into the curve to join input. And if we do that correctly, we should see the output as a single polyline again. So at this point, we've gone from the curve at the beginning, we've done the simulation on it, we got it out the back, and we've rebuilt all those segments into the final single curve. So at this point, something cool that we can do to get to kind of the graphic I showed at the very beginning of class is actually save all these states over time. So we can kind of record our progress as the simulation is running. So one component that comes stock with Grasshopper is this data recorder component. And with this one, it has, just like the camera, it has a recording button, and then also on the other side, a delete button. So with this, we can toggle on or off the recording button. And with this, we can actually record any data that's been coming into it. So we could record all these curves over time and build upon that to get something more solid. So I'll just go ahead and plug our curves into the recorder here so we can start recording. And I'm going to pull out a panel. This isn't necessary, but if you want to also see the data build up, you could also bring out a panel as well. So with the data recorder, if we have the record button in the orange on state and we start to animate our solver, we'll see some points populating the panel here, and they'll also be saved in the Rhino viewport so we can see them all as they come in. And if we want to do a different simulation, we can delete all the data coming in, reset the solver, make sure to clear it if there's anything coming up, and then we can simulate again and get that data all recorded in this component here. Okay, so at this point, with the file I shared with you, if you scroll over to the right, there's this little component just floating up over there. Should be to the right somewhere. Maybe it's above, but it's out here just on the canvas by itself. Let me know if you can't find it, but it should be over here.
Wait, how'd you get to it?
Yeah, so you can toggle this button here. So in the gray state, it's not going to do anything. If it's orange though, it'll start to record whatever comes into it. So it could be curves, it could be points, numbers, pretty much anything, and it'll save it. Yeah, it's just data recorder. Yep, right there.
Is that the report?
Yep. So as this line is shrinking down to something super small, I'm recording all those steps over time. So we can see the simulation as it's happening. You kind of record the progress there if you want to maybe check back on it later if you're doing something else. But in our case, we're going to actually use all these curves in the final model. So is anyone having problems with this step? Or?
When I first record, I mean, like that, you know, animate things.
Yeah.
Nothing's like,
Is the component previewed on? Or okay. Yeah. Okay. Cool. So yeah. So yeah, if you're all at this step, there should be a component floating up here, up to the top right. So if you just grab that and pull that down, so it'll be next to what we're working on. That's perfect. So the only reason I included this is because this is a C# script. So it's not something we could do today in class. So I just gave it to you all. But basically what it does is it's going to take all the curves and it'll pull them to any piece of mesh. So the reason why I'm using this is because right now we kind of have this piece floating around the figure, but I wanted to ground it on the mesh of the figure itself. So what we can do is actually take the curves and plug them in. So there. And then we can also take our mesh from the beginning as well and plug that into here as well. So yeah, this will look a little hard to follow along since it's from the start to the very end. I'm going to grab another mesh component just to make it easy to see, but you could also just drag the line straight to the back. Either works. Basically, just what I'm doing is typing the mesh into another mesh component, and then I'm going to carry this one along with me to the end, so everything stays a little clean. So this is just our input figure. And I guess little tip here, not super important, but little tip is, I mean, I have a plugin reading out the names, but I assume you all don't have that. But one thing you can do with pretty much any component is just change the name of it. So right now I wrote in a name, but it's still showing this little mesh icon here. You can hit this little paint bucket at the top, and it'll swap it from icon to the text you wrote. So you kind of keep track of things. But this is just our input mesh again. So I'm just going to plug that into the mesh part here. And then coming on the output of that, you'll just see that all of the curves that we generated before with Kangaroo have just been projected onto the mesh. And those are just showing up in gray for me right there. Yep, just whatever input you're using. I just use another component so I could kind of clean up the wires. You could just zoom out and grab it and kind of plug it in if you know what you're looking for. Yeah, I just grabbed the mesh and just moved it over. Yep. Yeah, so this just allows us to kind of ground all the curves on the face of the mesh. Basically what the C# code in this component is doing is dividing all the points or the curves up into a lot of points, projecting those points onto the mesh, and then reconstructing the lines from there. We could do that in Grasshopper, but it's a lot of components. So the C# script is super quick. And if you actually want to look into this, you can right click on it, edit source, and you'll actually see written code, but I try not to show any written code in this class, so we're not even going to go into it. But if you want to open it up and look at it, you can just do that from there. Okay, so at this point, we can do like I've done in a lot of the other, curve tutorials, is use the Dendro plugin to solidify everything and get us something that we can 3D print. We do this workflow, I guess this part, pretty much every class, but it's also might be super helpful for your final projects as well. If you want to do something like this, like a curve-based system, and you want to print it out, we can thicken it really quickly with Dendro and get a model that will print no problem. So we've done this a couple times before, but I'll build it through again. So always with Dendro, we have the settings. So we define the resolution of the voxels or the volume that'll be surrounding all the curves here. So we grab that. We grab our curve to volume component. So this will take all the curves that we have. We have two sets of curves at this point, the curves that we recorded and the curves that we projected onto the mesh. Yep.
Because when it's projecting, that's a very it just looks like it adds more lines.
So do you just have one line out of Kangaroo? Or did you simulate it yet? Is it?
I did. Well,
Oh, yeah. So I don't think you're recording anything. So that would just give you the one.
then also we.
Yeah, I
But
plugged
then it was like,
Yeah, so you'll have to turn on the record button and then do the simulation. It'll record everything. And then that output can go into the C# component.
oh, okay.
Yeah. And then you'll build up the curves over time to get something that looks more like what I have here. Okay, so yeah, coming from this, yeah, as I just mentioned, so both of the curves, so these curves and these curves will both be going into this component. So, we can grab a merge component just like we always do to combine multiple inputs. So we can combine those together into this merge block. And we can plug those all into the curve to volume to get that started. Okay, at this point, we need to define the settings, and we also need to define the radius for the curves themselves. So the best practice way to do that, since if you remember from the past, the settings here need to be 33% smaller than the radius of the curve for anything to generate. So best practice way to do that is to grab a division component. So we can just type in a / in the search bar with the division component in the scene. So with this division component, as I said, if we hover over the radius here as well, it'll tell us, or maybe if we get an error, it'll tell us, but yeah, just know that the radius needs to be 33% larger than the settings for anything to actually generate. So with this, you grab a slider. So I'm just gonna do like, I don't know, 0.1 to 5. We'll see if this works or if we'll have to make the range bigger later on. But for right now, I'll just start from, 0 to 5 as a range. We can plug that into the top of the division and also the radius for the curve. So we'll use this single slider to define both the radius of the curves and also the settings that the curves will be affected by. So we'll just divide that by, 3.4. That should get us down. Is that the best way to do it? Let me see. You could also use multiplication, but I think we're doing the same thing here. 0.2, well, not really, but that would work. But yeah, my bad. A better way to do 33% is to use the multiplication with the decimal. So I'm just going to swap out the division with the multiplication. Okay, so yeah, once we do that, we should have the correct setting for the volume. One thing though, I'm going to move this slider up to the max just to start. The lower we go, again, the longer it'll take for your computer to calculate the volume. So I'm just going to go as high as possible to start so we get a quick result, and then we can refine it from there. So multiplication will affect the settings into the S input. Then we can use these settings. So the S will go into the S for the volume curve there. And we'll start to see an actual 3D result around those curves. And then once we have that, we can start to bring this slider down or maybe up, depending on your scene. Yeah, that's why it's important to put that slider all the way to the max to start with, or it might take a lot longer. So let me actually, it looks like my curves are super thin. So I might go up to somewhere closer near 20, just try to see what's looking the best and then scale back from there. Yeah, at least it didn't crash on 0.1. So you only have a couple curves, so you were spared.
Is the number of curves? That's just gonna count for the beginning. Populate.
Yeah, so well, the number of curves you have now is completely defined by how many steps you did in Kangaroo.
Yeah.
So
That's the enemy.
right, so if you did more steps, you would have more curves in the final dendro. part.
But is there a way to like shrink the gap?
Yeah, so the best practice I've seen to do that would be to set your slider back to 0, so it resets, and then clear the cache in the recorder, then start the recording, and then slowly move your mouse on the slider up to, you know, whatever number. You can do as many steps as you want. It's completely up to you.
And then like.
With the animate,
Yeah.
yeah. So I have 0 to 100, so they're all integers. Usually the step is a integer value. So every whole number that you go up will do another step. Yeah. And then 0 is used to reset the whole system. So. Yeah, so what's your slider set at?
It's 0.
Okay. Yeah, so I mean, I went to 32, but I zoomed in a lot and like slowly dragged it up to 32. Because if you go quick, the slider, yeah, it'll skip values the faster you go, which sometimes can help you if you maybe set a number too low on the dendro settings and you want to quickly go up to the highest number. It'll skip everything in between. Another thing though, with your substeps in the solver, your substeps might still be at 10. So I set my substeps to 1, which you did as well, which usually makes it go a lot slower. Yours is jumping a lot. So. Yeah, well, that's the beauty of physical simulations. Everyone's going to be slightly different. Yeah. But yeah, as Susan refines that. So for everyone else, the very last step pretty much is one thing we can do is smooth the output from the volume curve. And with this smoothing component, we have an option for iterations here. So we can smooth more or less. By default, it's at a smoothing value of 1. So, you know, we could smooth it, say, 8 times. And we'll see the result. Let me just hide all this. We'll see the results smooth out a lot. So right now, the look I'm trying to go for this is might be a little bit too thick. So I'm going to bring this value down again. What else does that? Okay, so we can get it to something more refined like this, and you can play with all the values with how you're smoothing as well, and you know how radius, how dense your curves are, and everything like that. But this is kind of close to what I showed at the beginning of class. So this is kind of the output we're getting now. And since we set the goals as we did, and we used that mesh or curve to mesh component, we see nothing's going inside the mesh here, which is very nice. So everything's staying outside as it should. Is it going inside? You could have some of the simulation settings set up. Not all the way. Oh, yeah. So see with that solid, you have true set. So you're telling all the curves to go inside. Yeah. So that's probably why it's going really fast, because it's trying to get inside the mesh as quick as possible. Yeah. Yeah. So also it's, you know, if you're going to kind of change how your curves are going, it might always be good to also just turn off the dendro part. Yeah, just turn it off completely so it doesn't try to calculate every single time. And come back to the curves and affect that. So, oh no, like completely disable. Yeah, because preview, they'll still compute, which is not what you want. Yeah, so at this point, we have this whole script set up so that if we want to change the seed to something very different, we can reset the kangaroo simulation and it'll completely change the look of the final output. So all we do is affect the seed slider, get a very different seed. And then we can come back and reset the kangaroo and simulate again, and we'll get a different output every single time. And right now I'm kind of stacking up multiple different seeds on top of each other because I haven't reset the record component. So there's a lot of kind of play you have with this this workflow to get different results.
So the number, the 33% in the voxel setting, what is that?
Yeah, so in the past, when we've done this Dendro workflow, a lot of people have gotten the error, like their radius setting was, or I guess the setting for Dendro itself. So like this number was too big for the radius and it just wouldn't show anything. So the way we worked at it before is we had two sliders, one for the settings and one for the radius. But when you do that, you have to kind of control both at the same time to actually get something to show up. In this case, we just automated that second slider. So now the setting is always going to be within the range that you'll see something in Dendro. So you never have to worry about if your setting is the right number. You just have to set a radius and the rest will go. So.
Is yours just really close together?
Yeah, so my lines are really close together. One thing you could do is the whole nth value. So it calls every couple numbers. Right now it's calling every second number. If we plug in our data recorder to that, you'll see we'll go from dense curves to, if we call every other, we get less dense list. So if we do it like that and plug all this back in, once it recomputes, we'll probably see some more holes in between if that's the look you're going for. I was also affecting, the smoothing value over here as well. So that's something a little more organic, which might be nice. There's also a lot you can do with the smoothing. So right now it's smoothing a lot with this value of 8. So a lot of the detail that we had before is getting taken out by the smooth. It's just kind of glossing over it all. So we could lower these values and maybe get something more like the input. But with these values I have, it's going to be really, really smooth finish on the outside. So that's maybe something you like. But yeah, there's a lot of minutia that you can affect in the script and play around with to get to different looks. And again, with that seed value, you have infinite possibilities with what the output could be. So, you could spend an hour, trying to get to something interesting. So yeah, that's the first workflow. The second one, again, I mentioned, is also in this document. The second one is a lot simpler. We're just doing one simulation in Kangaroo. So I'll hop down now. If anyone's still playing, I apologize, but we're gonna move on to the other one and show that real quickly before 7 today. Okay, so if you want to follow along with the mesh flattening workflow, I'm gonna move on to that one at this point. So just we can get through everything before 7. So I'm in the same Grasshopper document. If you scroll down on the left side of the canvas, we should have this little group right here. which is basically just creating this surface as an input to start with. So if anyone can see that, let me know, but we're going to go ahead and start building this Kangaroo solver to flatten this out. So again, this one has a lot less steps than the last workflow. It's pretty much just a very basic Kangaroo to show a different function of the plugin. So okay, back in Kangaroo for this one, the first thing I'm going to do, since we have this surface already made, is pull out a solver. I'm just going to use the really basic solver this time so we can kind of see exactly how this one works as well. So again, we used step solver last time. Now I'm just going to use the basic solver. Nothing fancy to this one. So with this one, if you saw me when I brought the last one in pretty quickly, just to show an example. Again, we have the goal objects up top, which we will define. We also have this reset value and this on or off value. So with the last one, there was a slider to do everything. Now we have two inputs. So with this one, we need a button component, and this will just be our reset button. So every time we hit this button, it'll reset the solver back to 0. So it might be a little bit easier this time to just hit this to reset, which is nice. And then on top of the button, we'll also need a Boolean toggle. And this will either, if it's false, turn off the simulation or pause it. And if it's on, it'll run it, or basically like hitting play. So with those two, we can now define the goal objects. So nothing's going to happen at this point. We'll have to define the goals first. So I'm going to get a merge component to start setting this up. Same as the last one. Oh, actually, with this one, we're going to do something different. So delete the merge if you made it. We're going to do something a little bit more interesting this time. So we can actually interact with the Kangaroo solver as it's running with this workflow. So we use the component called entwine. So it works very similarly to merge, but the entwine, you can put things on different branches based on where you plug them in. So this will give us a little more control on the output this time. Instead of having to clean the bad parts, we can put all of the goals into one input, and we can actually put the geometry we want to keep into a separate input, so we can diversify on the output what we're actually using. Okay, so with this, coming back to the surface here, the first thing I'm going to want to do, because there's not a lot of usefulness for surfaces in Kangaroo, we basically can only work with points, curves, meshes. So the first thing I'll do is convert this brep to a mesh. So there's a component called mesh brep that basically just triangulates the surface into a mesh surface. So with that, just plug it in, surface into brep. Again, surfaces are breps, but breps are not always surfaces. But in this case, we can just plug surface into brep. We'll get a mesh out of that. Okay, so with this workflow, we have 3 goals, again, to define for this mesh and what we want it to do, and then a 4th extra special goal that will allow us to interact with the simulation as it's simulating. Okay, so the first goal will be this component called onPlane, and this will keep all the points that we define on a set plane. So for this workflow, again, we're taking this doubly curved surface and we want to flatten it out onto a flat sheet. So if, for say, you wanted to take a shape like this and be able to map it, say, on a sheet of paper or a piece of chipboard, so you could like laser cut it out, and you get this really weird flat shape, but you could fold it back to this shape. It's not a one-to-one comparison because we don't have any darts or pleats in here, but we can get as close as possible by taking this and kind of simulating it being flat on this plane. So onPlane's the first one. That'll just project the points onto a plane, but that really doesn't keep the shape of this doubly curved surface. So in order to keep the kind of shape and distances apart for that all the points are, because as we move down here, we're going to have a lot more detail than, say, a flatter part like this flat edge. So one thing we can do is divide the mesh into a bunch of small edges. And just like the last one, as we had a bunch of small edges, in this case, we want to keep all those edges the same length, but we want to project them on a flat plane. So places that are more curved will kind of spread out more as the edges stay the same length, but they try to all flatten out cleanly. So the next one we'll use is, let me find it. Okay, so under goals mesh, we have this edge length component. And this one's nice because we don't actually have to create the edges ourselves. Like the last workflow, we had to actually create all the segments for the curves. This one, it just needs a mesh input, so that's nice and easy. And then the last one that we'll need for this is the same one we used last time, so the sphere collide. So we want to make sure the points are kept apart. In this case, we're not going to be changing the radius, we're just changing how it's mapped. So we'll keep the length factor and the radii static at the same number the whole time. And then the last thing we're going to add in here is a special component, so we can actually interact as the simulation is moving. So under the main, just where we found the solver last time, there's this other one called grab. And this one's pretty nice because we can have these goals actually affecting how the mesh is moving. But as it's simulating with this one, we can actually grab the point, let's say on the surface, and pull it to kind of stretch the fabric out and make it more flatter, or pull it to a certain shape. So I'll visualize how that works later. For now, we'll just have that on the canvas. And last one, it's not a goal, but more something nice for the entwine specifically, is right under grab, there's a component called show. It's a little light bulb. What this one is doing is it'll take the input geometry, in this case, the mesh plane, and with the show, we can put it on its own branch. And then on the output, we can really easily grab that again instead of having to rebuild something like we rebuilt the curve last time. So the ones on the top and the bottom are kind of the special ones. The ones in the middle are the actual goals that'll be affecting how the mesh moves. Okay, so right now with the mesh, first thing we can do is just plug this into the mesh for the edge lengths, because that's consistent. We don't have to change anything. That can go right in. For everything else, we will have to do a little bit of editing to this mesh to actually get the data that we need. So the first thing we can do with this, first thing we need is the points for the points on plane, and we can use the same points for the sphere collide. So in order to get the points of the mesh, we can deconstruct the mesh itself. So let's just deconstruct mesh, and then if we hit those together, you'll see the surface and Rhino will update, and we'll see all the points that define the edges or the vertices in the mesh itself. So with these vertices, we can use these to define the points that we want to keep on a certain plane, and we can also define the points that we want to keep in the sphere collide to make sure they all stay the correct distance apart. We're losing stuff here. Okay. Okay, so at this point, we want to define the plane that everything's going to be mapped onto. So it's the easiest way. So we can use the XY plane because that's the closest plane to the shape that we already have. So again, if we look in Rhino, the XY plane is going to be pretty much this base grid right here. That's just flat right below it. So this is the easiest one to kind of flatten the mesh out onto, is this plane that's flat right below it. So we'll use XY right there, and then we'll be able to plug that into the plane input for the on plane component. Okay, so the on-plane component is pretty much finished up, so we can go ahead and plug that into the entwine, and I'm just going to put that on the second branch here, so 0, 1 for that second branch. And then we skipped over the first branch, but I'm saving the first branch for the show components. I'm going to go ahead and plug the show into the first branch, which is 0, semicolon 0 right there. So for the show component as well, as I said, this is the piece of data that we want to keep on the outside. So we want to get the mesh on the output. So we'll take this mesh from the input and just plug that into the show right there. So we'll be able to keep this through the rest of the simulation and just pull that out at the end. We'll see in a few more steps why this is actually useful. But this is a little bit more best practices, compared to the last one where we're just using a merge. So the entwine with a show, a little better practice here. Okay, so coming down to the edge lengths, the last two inputs here, so length factor and the strength. For the length factor, it's good where it's at because we don't want to change the length of any of the edges. We want to keep them consistent. So the multiplication factor of 1, we'll keep them all as they are. And for the strength here, though, this is an input that I haven't touched on yet, but the strength it comes with every single Kangaroo goal component. And this is basically telling the simulation, what goal is more important than other ones. By default, they all have a strength of 1, so they're all kind of equally ranked in the final simulation. But for this case, I really want to make sure that the edge lengths do not change so that we have the most correct mapping of this doubly curved surface onto a flat plane. So I'm going to grab a panel with 2 forward slashes and just use a value of 100 to say that the edge lengths are way more important than anything else. If the edge lengths stay consistent, then we'll get the closest flat mapping that we can. So I'll just create that panel and plug that into the strength here. I'll see you guys next time. Yeah. Sounds good. Little trap. Okay. So the last thing we're defining here is the radius of the spheres to keep everything staying apart from each other. And this one requires a couple more components to set up. So basically what we want to do is actually find the edges from the mesh. And as last time, we'll find the average, use that length as the radius for these sphere collides. So first thing we can do is there's a component called mesh edges. It'll look like this little box with a slash through it. This component will take a mesh for the input, and it'll give us 3 valences of edge conditions. So the first one is a valence of 1. So basically, this edge is connected to a single face. So in that case, what that means is I'm going to pull out a component here just to visualize that. So this is grabbing, let me turn some stuff off so we can see this better. You can't really see it in gray. Let me just change this real quick. Okay, so the edges with the valence of 1 means that the edge is only connected to one other face. So that'll be all the edges that are on the outside of the surface. So if we see the actual, and this isn't part of the workflow, but we can see actually all the edges in here, and we can see all the faces that make up the surface as well. So all these edges with the valence of 1 are the outside edges. Everything with the valence of 2 means it connects to at least 2 adjacent faces. So that'll be all the edges on the inside. And then E3, we have nothing in there because we have a mesh of quads. So there's no edge with a valence higher than 2. So explaining all that, basically what we need is we just want all the edges. So I'm going to grab a merge component and just merge together edges in E1 and the edges in E2. And that'll just give us every edge of the mesh. So with all these edges, just like the last time in the last workflow, we can use the length component to find the length of all these edges. And then we can use the average component to find the average value of all the lengths. So length component, plug that in. We have a list of, I have about 4,500 edge lengths here. And then with the exact same average component as last time, we can take all those 4,500 edges and get the average value, which in my case is about 4.67. So that's a good average here. We could be more specific and find an actual radius value for every single point, but just to keep it simple for today, we don't have quads that are too different in size. They're all pretty similar. So we can just use this average value as the radius for the sphere collide. Okay, so at this point, everything should be set up. So we have these last three goals right here that we have not connected to anything. So we can connect all of those to the same input 0, 1 here as well. So I'm just going to hold shift as I'm dragging. We'll get that little green arrow that comes up on our mouse. And we'll just hold shift, click, and drag all of these outputs from the goals into the input of 0, 1 right here. So we have the show going into the first input and everything else going into the second input. So with this, it's all set up now. And we can just take this straight into the goal objects here for the Kangaroo solver, and everything is ready to go. So I'm just going to hide everything we don't need anymore. Okay, so we're all ready to go with this. So one thing I do before starting a solver every time is just hit the reset button. So all the values are now reset. And then we can just hit the double click for the toggle, set that to true, and we'll see that the simulation will start to go in Rhino. And one thing while this is going, unlike the first workflow we did where the curves were just doing their own thing, now that we've added this grab component, we can physically grab any of the points in this kind of mesh. And while it's simulating, we can pull them and stretch them. So maybe if there's a part of the mesh that isn't really flattening correctly, like we have a little overlap right here, we can go ahead and grab one of these points and just pull it out, kind of untangle it as it's moving, and just drop that back down, and the simulation will keep going. So all the points are staying away from each other, and all the lines are trying their best to stay in the same length as they started. So over many iterations, I'm just going to stop this right here. We have about 1,400 iterations in this simulation. You could let it run for longer and it would become more perfect, more flat. But for this case, it's close enough right here. And you'll notice, like, if we look at the input surface versus the one that we've just simulated, all the points with the most curvature have bulged out a lot because we have more, surface in that area because it's going down farther. So we have a bigger bulge there. With this final one, if you wanted to take this, into Illustrator to get a DWG, to get a cut file for a laser cutter or something like that, there's like 3 more steps to actually get a file that you can just send straight to a laser cutter from Grasshopper. So with the output here, since we've used this in Twine, a bit of a smarter method, now all we have to do to grab what we need is we can use explode tree explode. It kind of looks like this orange palm tree right here. We can grab that component. And what this one is doing is basically taking the branches that we created with the entwine. So we had branch 0, 1, and 2. And this will put branch 0, 1, and 2 on their own output here. So we have in the first one, just the mesh, which is pretty nice and clean. Second one is all the goal objects. So we really don't need these anymore. They were just for the simulation. All we need is that mesh. So that's coming out in 0, 0. So again, with the mesh edges component, same one we used before. Now this time the valences are necessary because in this case, if we want to, say laser cut this flat stock out, we only need the edges lining the outside of this shape. So if we plug these together, I'm just gonna hide everything. If I grab, a data component in E1, we can see we now just have the outline of the mesh that we simulated. So with this outline coming out of E1, so the valence of 1 where the lines only connect one face, we see that the outline is not perfectly flat because we didn't get a perfect solution. We could let it run for longer and it would get better, but it can't run infinitely. So do one thing to clean it up. So at this point, in order to make it completely flat, we can just go ahead and project it again on that XY plane that we defined earlier, and we'll get a perfectly flat curve. So I have this project component. There's a couple with the same name, but I use this one because we can project any object onto a plane. So with this one, we have the object of the curve, and we have the object of the plane from earlier. So we can plug the curves into the geometry to project. And then for the plane to project onto, right now by default, it's XY, which is perfect for our needs because we're using the XY plane. So we can just go ahead and hide kind of the edges from valence 1. And we'll see that now we just have smooth flat edges on this XY plane right here. So now you could make this as a curve, just export it straight to Illustrator, or the last thing we could do is use this component called boundary surface. And all this needs is an outline to make a surface from. So if we plug those together, we can basically fill in the surface here and get a filled shape. So either one is useful. But I will show just for the end of this workflow, if I can pull this away. So with project, if we were to, I'll actually join all these lines first because I'm seeing that we have a lot of lines coming out of the projected geometry. I'll join them all first. So now we have one polyline curve. If I was to bake this into Rhino, I have one curve here in Rhino. So what I can do to, send this to the laser cutter really simply is I'll switch over to top view in Rhino. So you might have 4 windows open already. If you don't, you can double click always on the name of the view up top, switch to all 4. And I'm just going into top view right now so we can see straight overhead. So with the curve selected in Rhino, Rhino makes it really easy. We can export selected from here. And, we can save it wherever. But we can actually save this, where is it? As an Adobe Illustrator file. So we can just save it straight from here as a .ai file. And then you can take this into Illustrator, set up the lines as you need for what they require for the laser cutter. Or if you just want to print this out on a piece of paper and cut it by hand, you can do that as well. But yeah, super nice. We can just bring this straight into Illustrator and edit it from there. The reason I go into top view is because once we, save it as an Illustrator file, it'll ask us for the scale of the model. So we could set the scale in Rhino. And if we're doing that, then we want to preserve the model scale. So 1 millimeter equals 1 millimeter, or, you know, whatever units you work in. And then we can define kind of the color space and how the layers work right here, and just export that straight as an Illustrator file to open up later. So again, you can pretty much do this for any surface. Let me see. In this case, we've taken this crazy curved surface and flattened it as best we could. And if you print this out, you can get back to that shape for the most part. But yeah, that's one other way Kangaroo can be used. You know, I showed a lot more in here if you want to do tensegrity or, you know, simplicity with surfaces or things. A lot of other opportunities with this plugin, but that's just a few things I wanted to show today. So that's it for the workflows. As I said at the beginning of class, you know, next class, if you can bring in some ideas of what you want your final project to be, we can talk about it for, you know, 15 minutes at the beginning, just so you get a good first step in the process done. And we can go from there. But yeah, that's it for class. So yeah, thanks everyone. I'll put this up on YouTube a little bit later.
Thank you,
Yeah.
RJ.
You're welcome.